and welcome to today's webinar, DDR Design Guidelines, What You Need to Know to Achieve First Pass Success. My name is Brianna Curl, and I will be your moderator for today. Before we get started, I'd like to address a few logistics and details on the GoToWebinar platform. If you are unable to hear the presenter or see the presentation at any time throughout the webinar, please let us know in the chat and we will do our best to resolve any questions. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly during the webinar. This webinar will be recorded. The recording and the presentation slides will be posted on the EMA resource page. With that being said, I want to thank you all for joining us for today's webinar and introduce you to our presenters, Jerry Long and Orland Bates. Jerry is a Senior Applications Engineer for EMA Design Automation. He provides high-end customer support for several Cadence products, as well as product development and technical marketing guidance for the Timing Designer product. With a bachelor's degree in electrical engineering from the University of Texas at Austin, Jerry has been involved in several product lines involving verification, simulation, and timing analysis. Orland is a Senior Field Applications Engineer and has been with EMA since 2002 and has been in the PCB design field since 1973. Orland attended vocational tech school, earning a degree in drafting and design technologies. With many years of printed circuit board, printed wire design, DFM knowledge, and high-volume manufacturing, Orland is a highly skilled professional in the field of engineering physical design. Jerry and Orland will both be collaborating throughout the presentation and the demonstration. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now, over to you, Jerry.
Thank you, Brianna. So our topic today is DDR. I'm going to present kind of a brief history of DDR, how it evolved, where it came from, and then kind of discuss the families of DDR, how it's evolved over the years since its development. And then we'll focus on DDR4. We'll go through common challenges, electrical layout techniques, constraint requirements, things like that, how to basically get the best design results with the DDR4 flow. Then we'll go into a brief demo. Orland will demo some basic layout techniques, some basic layout capabilities. I'll briefly demo some simulation techniques and simulation capabilities that the JetX spec for DDR4 recommends. And then we'll wrap up with kind of a presentation of DDR5 and where the technology is going in the future. So DDR, basically what it is double data rate. That's what the DDR acronym stands for. It's basically a double data rate version of the dynamic random access memory that was developed many years ago. Standard DRAMs, as you probably remember, were originally asynchronous, and now with the new evolution of the technologies, they brought in timing synchronous capability to the technology. And then the double data rate comes in as they've been promoting the technology to provide both rising and falling edge clock edges for data synchronous to both of those writing edges. So you get essentially two words for every clock cycle, one on the rising edge, one on the falling edge. Double data rate devices are all source synchronous, and basically what that means is that when you're presenting data to a memory device or a controller on a read operation, you're also presenting a strobing signal. So this particular synchronous signal allows either the controller or the memory device to latch the data in. And presenting a source synchronous technology like that is much easier on routing techniques and timing and things like that. So that's where DDR, the base technology DDR has evolved from. There are 4 generations currently. The 5th generation is in development, and they do have a couple of devices out, I think, these days for the 5th generation. But the 4 generations look, we'll discuss that here in just a second. I kind of wanted to show a little bit about the specific meaning of double data rate and what that looks like on a timing protocol. So when you present data to a memory device or receive data from a memory device during a read operation, for instance, in the past you typically get one data word per clock cycle. So it's synchronous to the timing source, the clock, and you get one cycle, one data word per cycle out of that interface. Double data rate kind of doubles that up, as the name implies, where you get a data word on the rising edge and then a data word on the falling edge. You also have strobe capability now, as you can see in the timing diagram. There's a DQS line which gives you that strobe, which is that force synchronous capability, and those two signals are the important routing and timing signals for all of your particular design applications for DDR. Over the years, DDR has evolved. The first family came out in 2000. It had a basic transfer rate of anywhere from 200 to 400 megabits per second. Densities up to 1 gig. It had a 2N prefetch width, and the originals used just a single-ended strobe signal. So the clock was differential, but the strobe itself was single. It had a supply voltage of around 2.5 volts. And it used the SSTL technology for the IOs. The latency on these devices were 2 to 3 clocks, which was relatively typical with DRAMs at the time. And there were no on-die terminations. In other words, you had to terminate your data and control lines with discrete devices. DDR2 came about in about 2003. Data rates up to 800 megabits, essentially doubling the transfer rate. Densities were about 4 gigabits, up to 4 gigabits, and prefetch width now has doubled, so you get a 4N prefetch width, 4 words per transfer. Now with this family, they offered the strobe type in either single-ended or differentially ended, so you have the option there for your designs. Differentially ended was preferred essentially as you speed your data rates up. Differential ending is going to be a more robust signal. It's going to be cleaner. It's going to allow a better clocking source for the data transfer. Supply voltages are now dropped down to 1.8 volts, and you're still in the SSTL IO technology. Latency has increased to about 5 clock cycles, and now on-die termination has been presented for or offered for DDR2, and this allows you to kind of avoid using discrete logic for terminations. You can now take advantage of what's in the devices themselves. DDR3 came about in 2007, bumping rates up to 1.6 gigabits per second, densities to 8 gig, prefetch widths again have doubled. Now this is clock and strobe type are differential only, so it's an exclusive differential signaling capability there for the strobes. Supply voltage now has dropped to 1.35 volts, still in SSTL technology for the IOs, but now with the latency increase of 10 clock cycles in this particular family, and on-die termination is offered for this as well. And that brings us to DDR4. DDR4 was first developed in 2014. The transfer rate essentially is up to 3.2 gigabits. And then the densities here again have doubled to 16 gigabits. Prefetch width pretty much stayed the same. We'll go into reasoning there, but that more is an official, or is like an efficiency situation there. It's through smaller word accesses. A large prefetch was considered not very efficient, so they left the prefetch at 8N. Again, differential clocking, differential strobes. Power has dropped to 1.2 volts. And now with the increased speeds and the less margin for error, the less margin for setup and hold for data latching, the I/O has changed to what's known as POD, or pseudo open drain. This is much faster. We'll go into a little detail about what that's all about. And latency now is up to 10 to 15 clock cycles. For this family, on-die termination has become dynamic. So now you can have a particular transfer situation where your terminations are set for one way for a read, for instance, and maybe another way for a write, or a particular situation where you're accessing one device and all the idle devices are at a different termination. So you can kind of move around and program your on-die terminations based on your situation. DDR5 was first available at the end of last year. There's a couple of manufacturers, I believe, that have some devices available. But again, you can see DDR5 is again doubling the transfer rate, doubling the densities, and lowering the voltage. So we'll talk a little bit more about that as we move forward. So with DDR4, what has improved from DDR3? This kind of focuses on everything that's different in the DDR4 family. So naturally, everything has gotten faster. Density is larger and power less. But basically, the 1.6 to 3.2 gigabits increase and the density increase requires that there's a bit of technology change in the family to be able to accommodate successful operation for these devices. This is just kind of a summary of everything that's not necessarily everything, but the major things that were changed in DDR4. So we'll kind of walk down this list here. So the first thing is the VPP supply. So up to now, VDD supply handled just about all of the operations, all the internal workings of the device. So it required somewhat of a robust supply. With the DDR4, they now have a VPP supply, which basically powers the internal word line in the device. And essentially what that does, it takes the high current requirements sometimes of the internal DDR4 operation. It takes that high current requirement since it's not done that often and offsets it to a different pin. That way your VDD pin can run at lower voltage without as high a current requirement. And what that gives you is approximately a 10% power reduction overall on the device operation. So that's one of the things that changed with DDR4. Probably the most phenomenal change there, or robust change, is the I/O technology. It went from a push-pull arrangement, which is what the SSTL technology offers, over to a pseudo-open drain. The advantage here is that if you look at push-pull, you're consuming power in either state of the bit for the data bus, for instance. So in the high state, you're running through one MOSFET, and the low state, you're running through another out of the output drivers. With pseudo-open drain, you're only consuming power in a low state. So when you're driving the bit low, your MOSFET is turned on, and therefore you're consuming power through the pull-up there. And that's the only time you really consume a significant amount of power, relatively speaking. So in the high state, it's almost no current drawn at all. So you're just pulling up to a high value on the data bit, and that basically cuts in half power requirements for the driver. It also gives you the opportunity to implement what they're now referring to as data bus inversion control. And what this does is when you're driving onto your data bus, a data word that may contain 4 zeros or more in terms of an 8-bit data word, you can invert the bus to reduce the amount of power requirement that the data bus is going to consume. So what happens is the controller will invert the data word before it goes out on the bus. The data is transferred to the memory receives it, and then since the DVI bit is active saying that it needs to reinvert the data, it will reinvert before it brings it into the memory array. And so this does a couple of things. One, it makes for much lower power because you're transferring less zeros and you're switching less zeros. The other is it's much cleaner power because you have less current in adjacent data lines. So you're going to get a much cleaner data eye and much less noise in the data transfer. There's also been some enhanced error detection improvements. Data cycles, you can do cyclic redundancy checks, a much improved CRC code flow in the data side. Command and address bus now has parity bits, so you get much more accurate data transfer. There's been some other things like, for instance, an ACT control pin, which basically allows you to multiplex the address bits. Just a couple of the address bits, some of the high-end address bits are multiplexed with this control. They've also removed the VREF DQ line, which is the reference input for the data bus. This is now handled completely internally, and so it's not as additional pin or additional current requirement for the device. So all of these new technologies present challenges when you're building your design, when you're routing, when you're placing components, when you're laying out the board. Some of the technology, because you have to be so aware of what you're developing, what you're designing, they can be very time consuming. So you have timing issues to deal with, routing issues to deal with. I'll turn this over now to Orland Bates, who will discuss a little bit about how to go through some layout tricks and tips.
All right, thank you, Jerry. So let's look at the challenges with DDR4 component placement. If you've worked in the past with DDR2 and DDR3, that being on board or a DIMM card that you're designing, termination placement is very important. You will notice in the DDR4 section, now termination is at the very end of the completed routing for the command, address, and the diff pair clock nets. The need for less termination is a plus in the overall cost reduction. It's also a plus on freeing up space on the design and less routing for us to have to deal with. If you have a memory controller with read-write leveling, it helps greatly in the routing because this type of memory controller equalizes the timing. It sends a signal to the DRAM, and the DRAM sends a signal back to the controller. The controller can measure this delay at each DRAM and initially, internally, adjust for differences up to 20 picoseconds. We must now think in picoseconds, no longer nanoseconds in time. Again, this must have a memory controller with a read-write leveling. So what is registered memory, or to show my age, buffered memory as we used to call it? It is a registry between the DRAM module and a system memory controller, or could be built into the memory controller. They place less of electrical load on the memory controller and allowing single systems to remain stable for more memory modules than they would have otherwise. Now, memory controllers without read-write leveling is still a registered or buffered. The DDR4 component placement looks a lot like the old DDR2, DDR3 in placement of termination. Now, the termination takes up much more real estate, adding costs for the components. Routing becomes more important. Remember, we're routing in picoseconds, no longer in nanoseconds for time. Now, memory controller with read-write leveling and registered or buffered placement now takes on a different need. That having the termination at the end of each DRAM bank. This is what you will see in the demo that I'll be doing later on. Termination could also be built into the device, as Jerry pointed out. So placement is no longer just drop them down and hook them up. The physical design engineer needs to know what the components are, their function in the circuit for placement and routing to achieve this first pass success we talk about. Constraints must be defined and managed. Knowing the board stack-up is very important, and where the routes of the differential pairs and the desired impedance control. These layers to be routed on, the memory banks so that they do not permit crosstalk and to prevent noise, the min-max propagation delay, the relative propagation delay, so the clocks arrive at the same time the data lines and the strobes arrive is very important. You need to have software that allows you to manage this fast and check your work as you route. Also assist you in doing this work of the routing and correcting the flight times. I will be demonstrating this tuning assist also. The constraint manager for the electrical engineers. I wanted to touch on this briefly, but we've already done a webinar on this, and that webinar is called Managing PCB Design Complexity. So you can look that webinar up. But notice here that it allows you to come in here in real time using the pop-up to design your DDR. It allows you to control right up front by just typing in the areas you need for the spacing between lines within the byte lane, spacing between the lines from byte lane to a different byte lane. And it also allows you the line spacing for pins, a line for surface mount, also the line to via, line being your etch, of course. So at this time, I'm going to pass this back to Jerry.
Thank you, Orland. So once your layout is done, the next thing is to simulate what you've done on the board to verify that you're going to get proper operation and an expected data quality. DDR4 presents challenges to the classic signal integrity tools that most people have used to date, mainly because of the clock speeds or essentially a combination of the clock speeds, which equates to faster data rates, but also the drop in voltage levels. Both of those combine to give you less margin for error. The data rates give you less margin in terms of setup and hold presentations for latching the data. The lower power gives you, or the lower voltages gives you less margin for any kind of noise present in the system. So your noise budget decreases and your timing rate decreases. So these things are somewhat challenging for the classic approach to signal integrity. This is why the JEDEC spec emphasizes using serial link design methodologies to look at the performance of your interface for DDR4. It's very critical to analyze these layout results, this particular serial link analysis in mind, mainly because this allows you to essentially mock each data bit as a channel where you can send a large amount of data bits, typically 100,000 or so data bits down each individual channel line in a short amount of time. The channel technology is a little bit different than full-on time domain analysis that you normally do with a parallel bus interface. The channel approach allows you to essentially use a lot of data bits down the channel in a reasonable amount of simulation time. So that's why this is particularly favored to analyze the DDR interface. One of the enemies of this interface is simultaneous switching output, simultaneous switching noises. I mentioned the voltage drop basically reduces your margin for any kind of noise on the system, and the ability to switch fast with low impedance power delivery networks is going to affect that also. You can kind of see in this image here, when you have noisy power, you sometimes get not consistent wave transitions on your data line. So you want to make sure that your simultaneous switching noise has been either lowered to where it's almost non-existent, or at least well compensated for in your power delivery and network design. So that's one of the things that needs to be looked at in your DDR4 interface. You need to be power aware there. The other item to keep in mind is the sheer amount of interconnectivity between the devices. You have a lot of devices communicating back and forth. You may have 4 memory arrays that communicate all at the same time. You have terminations, you have other control lines, and then you have the power connectivity as well. So you need a topology environment, something that gives you a clear view of your system connection and understands all the connectivity between everything when you begin to run your simulation. So something like a topology approach, where you can put together all your IBIS model connections and your PCB parasitic models and have them all interact together is the best approach to take for this.
Thank you, Jerry. So now I will pass the screen over to Orlin to start our demonstration.
I sure am. I thank you for that. What we're going to have is, I went ahead and, to save time, did the placement with some first memory bank. I've got that placed, and I got the termination in there at the end. This is going to be routed in kind of a C horseshoe fashion on there, but I need to get the rest of the chips on here. Now, following our flow, I need to do a placement to get the rest of the parts on there. I can go in there to do a quick place. Under the options, you'll see here's all my components that I need to get placed on there. So I'll go in there and use quick place to save some time. There's 80 parts that I need to get placed on here, and I'll just say placed. I'm having it placed in the upper left-hand corner of the board outline is where it's going to place. So I'll just quickly place that. And then I'm finished. I can say okay to that. They've all placed. Now I'm going to make sure that I'm in the application mode of place edit. I'm just going to come around here and put a box over these components. So I want to go ahead and grab those components. And at that point, I can go in here and I can use a replicate that I've made, a memory bank. So I can create that memory bank, already have created it. And there's my memory bank there. I can apply that memory bank. And it gives me my parts, exactly identical to what I've already got. And that allows me to come out here now, and I can either place them down using the cursor, or I could come down in the command window and type the command into the exact XY location I would like that placement to exist. I'll go ahead and place those down. Now what we have here is ready for routing. This is the section that I need to route of the memory. Everything is matching. With that, I'm going to go ahead again to save time and pop up the board where I've already got it routed. Now I've got it routed, but I was interrupted a couple times during the routing of this, so I want to go back and make sure that everything is complete, and I think I need a little work between these two memories. So what I want to do is go ahead and come up here, and I'm going to actually go in and look at my timing vision on this. So timing vision is going to be able to tell me if I've got everything, the delay tunes in there and everything matched. Let me come over to my options window here. All right, so everything that is timed is going to be green. If I'm a little short, it's going to be red. Smaller amounts and longer is going to be yellow. And what I'll do is go in here and just grab these nets. I can just grab them all right through there. We'll grab everything that I need. Notice that I'm green on everything but this area here, which is where I thought I'd left off working on. So I need to go in here and actually get that tuning done. So I'll go ahead and just clear that section out now. And let's zoom in here so you get a better view of this. And what I want to do is come in here and tune this. Now I'm going to go ahead and change some of these layers out so that you can just see what I'm working with. It'll make it a little clearer for you. This is the tuning that I need to do here. So what I'm going to do is come up to my route command, and I have my auto interactive delay tuning, and that's what I really want to use. I want the system to assist me and get that tuning. So I'll come in here and just grab those nets and let it go in there and do the auto tuning for there. And it's complete. Now when it's complete, I wanted to go ahead and just back out of here. And if I back out of here, let's turn everything back on again. Now I want to go back up and recheck to make sure this hasn't changed, but I'll show you there. I'll go ahead and put a window around it now. Now I'm expecting everything to be solid green. There we are. Everything's ready for me to complete this, pass it over now to Jerry so that he can start simulation on this board.
All right, thank you, Orland. Let me get my screen here shared. So this is the same board as Orland mentioned. I've loaded this up in one of our signal integrity tools. The point here of what I'm going to do is to do the simulations. Essentially, you need to first extract models of the parasitics of your layout. All the layout work you did, you need some type of model that represents any of the delays and coupling interactions and things of the signals. We are interested in this section of the board right here, so that's where I'll zoom in and focus my my attention. Again, this is the controller over here. These are the memory banks. And again, as Orland pointed out, the memory flow is essentially this way. So the first rank will go through these 4 devices. The second rank will go through these 4. I'm going to focus just on this one because it's kind of redundant going through setup of various data lines, to whether you got 64 or whether you got 16 or 8. It's basically the same thing. It's just you know, you're repeating yourself more for some of the other modeling when you go with bigger widths. So I'm going to focus on just 16 bits. I've already got these the nets enabled. So with this particular tool, what you do is when you load up the board file, first thing you might want to do is check your Stackup. Just make sure your Stackup information from your board database is correct. So this tool allows you to do that. You can also do, you know, some quick what-if analysis if you want to do, you know, maybe a thinner dielectric or something. The next the next step is to select your nets, and you can see I've already got these selected. I've got 16 data bits and then 2 strobes, so I've got basically two byte lanes, and each of the strobes on those byte lanes. I've also got selected here the ground net, which is here, and the power net. So I'm going to do a power-aware extraction. So this will have the power delivery network that is being used to power up the controller as well as power up the memory devices. So that will also be included in the extracted parasitic model. If I choose to have the decoupling capacitors part of that network, I can. That's what this next step allows me to do. I'm going to skip that step here just in with respect to time. But this is just something that you can do. You can use realistic capacitor models for all your decoupling capacitors just to make sure your power delivery network is the most accurate representation in your simulation. After you assign models, the next step is basically to tell the tool where you want ports generated. Ports are, if you look at the layer selection here, and I'll just kind of zoom to these sections where these particular nets are, right here and here. These are the two layers where the nets have been routed, and port connectivity is going to, once I extract this model, I'm going to need connections on the memory end of all of these particular traces, and I'm going to need connections on the controller end, and that's essentially what the port generation does. It provides a terminated network connection point for each of the nets, and this is where I hook when I go and begin to run simulation patterns. This is where I hook my IBIS models up to, is the controller end of the ports and the memory end of the ports. So that's what generate ports does. It comes in, allows you to do that. I've already generated these. I'm just going to open them up and kind of show you what was generated. But you can see the ports. I've got a variety of ports for all of the data bits and the strobes, as well as my power line for the controller side. That's U34. And I've also got the same thing on the memory side. I've got a power connection, and I've got 16 bits of data and 2 strobes. So that's my port connectivity that I'll use to extract this model and then move to my next phase. So once I get that, I've told the tool the net connectivity I'm interested in, the port generations that I need for those nets. Next, I want to tell the tool, when you generate this model, make sure you make this model qualified over a certain range of frequencies, and that's, in this case, I've set that to 0 to 2 gigahertz. So that's my operating range that I want this particular model to be responsive through. So you can set that up. It's going to use an adaptive sweeping mode when it generates the model. And that's the last step in setup. Next, I just click off on the start simulation mode. That begins the frequency domain analysis of this, and it will generate me an S parameter model of my board connectivity between the controller and the memory. Once that's finished, I can just switch over to my network display. I've already got this loaded up after it's finished. And you can kind of see the network S parameters that this generated. So you see the power plane response up top. What you're looking at right now is basically the return loss of all of these particular nets. So you see the power connections up top. This is what the power rails look like. In my S parameter from up to 5, this just shows up to 5 megahertz, and as well as the data bus. So now you can see the data bus generation as well. It looks pretty clean, pretty consistent amongst the bits. These 2 outliers here, those are my differential pairs for my clock signals. You can also look at insertion loss. If you select the network here right now, as I said, you're looking at return loss, but you can also look at insertion loss. If you look at that, then it's going to switch to an insertion loss perspective, where you can see your connectivity for your data looks pretty well connected. Everything looks to be getting through fairly well unimpeded. Everything else, your power rails and everything are down below here. So once this is generated, you now have a network representation, an S parameter model representation of your board parasitics. So now what you want to do is go over to your System SI tool, which allows you to put those models together and begin to run essentially data patterns on them. So this is the topology tool. You basically put together the topology of what you want to simulate. So I've got my controller model, my PCB model, which is what I just extracted using the Power SI tool, and then my memory model. Both the controller and the memory model are IBIS models. So if you double click on each of these blocks, you'll get the configuration panel here. This allows you to navigate over to whichever model you're going to connect that to. In this case, it's an IBIS model for the controller. Same thing with the memory device. You double click on that and make an assignment for that. That's your IBIS model for your controller. Your PCB block will be what was extracted using the Power SI. This is your extracted model. And in this case, it's an S parameter network that is basically generated from Power SI using a SPICE wrapper. That's what this CKT file is right there, and that's how that gets generated. So if you look, that's assigned to that circuit file. So this is basically a SPICE wrapper of an S parameter network of my board layout. So now I have an IBIS to my board over to an IBIS to the memory device. I've also got a power supply in place. This is my VRM. It's going to run at roughly either 1.5 or 1.2 volts, depending on what technology I'm using. But that's what the VRM is going to do. It's going to power that PCB through to the controller and through the memory, and then give me an accurate representation of my power delivery network performance through this particular layout design. So again, just like PowerSI, what you're doing is you're walking through this workflow system. So here I've defined the workspace. I've already walked through the IBIS model assignment, which is what this step is. The next step is editing model buses, which is basically your PCB, assigning those models, assigning your power supplies. Now I've got the connectivity defined. What I want to do now is go and set up my timing budgets. So this is where I go in and tell the tool basically my data rate I'm going to simulate at, any of the setup and hold margins I want to try to meet by setting these margin values here during a write and then again during a read operation. Setting these margins gives the tool something to compare to. It gives it a constraint to show margin against when it does the simulation. It'll show you basically how well it met what that requirement was. So it shows you that immediately by applying those. So in this case, my data rate is going to be 3.2 gigabits. The next step after setting your timing budget is your analysis options. And this is where you set, in your IBIS models, this is where you set your driver technology. In this case, we're running all DDR4 technology with on-die terminations for all the data bits at the controller. And so that's my first byte lane. This is my second byte lane down here. This is my stimulus pattern. I've set it to a random pattern because I'm going to use my channel simulator to run this interface. I'm going to go through and use channel simulation technology for this particular flow. Switch this over to memory, and again, at the IBIS assignment there, you can assign whatever drivers are going to be pertinent to the data bus. Again, we're running DDR4 drivers with on-die termination settings here that are in the IBIS file. So that's the driver termination sets that we're using for this particular simulation. Over here is where you indicate whether you want to use a channel simulator or not. I'm going to use the channel simulator. If you don't use the channel simulator, it's going to give you a standard pattern, a standard time domain simulation flow. By using the channel simulator, it's going to treat each data bit as a discrete channel. It will essentially qualify that channel and then use the convolution algorithms of a channel simulation techniques to go and run up to 100,000 bits down that channel. You set that information here in the channel simulation tab. You can have it ignore a certain amount of time once the simulation starts so that each channel can stabilize. You can specify the least amount of bits that you want to run down that channel. And in my case, it's 100,000 bits that I'm running down there. Your sample rate, you can specify a noise floor if you like, and then the number of bits for display when you're looking at your eye diagram. I'm going to look at roughly 100 bits of performance at the tail end of the simulation. So that's kind of what that setup's all about. So once you set that up, the next thing to do is essentially go through and look at I'll go ahead and close this. The next thing to do is look at your connectivity to make sure all your connections have been made, and that's what the check signal connectivity is all about. What that does is go through, it does a quick frequency sweep on each of the bits, each of the connections to make sure you have a valid insertion path through there. So it looks at just a quick frequency analysis and an insertion value for signals propagating through for each connection point. Once that's done, you can terminate any of the nodes that you may not be using, may not be activating in this simulation, and then kick off a bus simulation. So I've already done that. I'm going to go over to my browse results, and that's what's showing down here now. So I've essentially got basically two simulations that I did. With the DDR and DDR4 essentially and channel technology that you're running, channel simulator technology, you have the option of using and utilizing some receiver algorithmic modeling interfaces, and that's what I did. Is I ran one without the AMI connected and one with the AMI connected. So we can take a look at both of those. And real quickly before I enable those, to put AMI activity into the simulation, and with DDR4 it's just on the receiver, and I'm doing a write operation, so it's going to be on the memory side. I would come in here and do a right click on the block and just add an AMI terminal. And so once I've added that AMI connectivity there, then I can double click on it and then set any kind of equalization that I want on that particular receiver. So I can set some AGC, for instance, maybe some taps on the CTE, number of taps, the gain, and the DFE kind of thing. So all of these controls are available through that AMI interface. And this particular tool has the ability to create its own, you can create your own AMI models if you like. Just choose from a set of standard installed libraries that you can set up with some of the standard functionality for AMI. So you can choose to use that, or you can also obviously choose to use the vendors, you know, for the in this case for the memory on a write operation. You might have a vendor AMI model that you've gotten and want to apply that in your simulation. So that's how I ran. I ran once without the AMI and one with the AMI enabled, so you can kind of see the differences in the improvements that the AMI might make on the receiving end. So let's take a look at those. I'll just hit the show results here. It's going to bring up the results that I've already ran. Bring this down a bit. So this is the standard default display. You see your topology up here. You'll see a channel report over here. This is basically just your report file. We'll take a look at each one of these. This is a three-dimensional eye density chart that you can look at to see how clean your eye looks. But what we're primarily interested in is this right here, your two-dimensional waveform display. So right now I've got both waveforms present. So here's all the waveforms. I'm going to turn, I'm looking at the package pin. So I'm going to turn the response to the die pads. I'm going to turn that off and minimize that. And then minimize this one as well. And then I'm going to switch on just the responses at the package pins. That's kind of what I'm really interested in, is what everything looked at the package pins. So I'm going to go ahead and turn on the package pins here. And this will show essentially the waveforms that were in response. I'm going to turn the strobes off to kind of clean it up a little bit. And then the power and ground, I'm going to turn that off right now. And then I'm going to switch this over to eye diagram format. All right, so this is my eye diagram of both runs, the AMI and the non-AMI version. So you can kind of see that there's some bits in here, and most likely if I come up to look at my no AMI first, we'll go ahead and just shut this one off. You can kind of see once this clears out here. So this is just the non-AMI run. And you can kind of see there's some bits in there that are somewhat problematic. Maybe you want to take a look at what you can do to fix it physically. But there's also the option of AMI. In this case, AMI cleaned this up pretty good. So here's my original. And then I can go ahead and turn my AMI or my no AMI run off and just take a look at my original AMI or with the AMI intact. Just minimize that. So now I can look at everything on this guy for data low and upper data byte lane and lower byte lane. Turn the strobes off, so we're looking at just the data. Now you can see it's a much cleaner eye. And once you get to this point, you can actually come in and turn on masks. I've got one defined for this particular device I'm using already, so I can turn that on, and now you can see the eye mask that can be put in here, and you can see how well you're meeting this particular JEDEC standard for this speed grade of device. You can kind of see how things are looking at for this. So that's pretty much the simulation I kind of wanted to go through and show you. Remember, it's the flow basically is grabbing an extracted model of your board parasitics and then placing them into a topology format such that you can drive stimulus into them with IBIS models. The PCB is the extracted model from my board, and you can also include your power parasitics, you know, from your power delivery network. With that being done, I'll go ahead and pass this back to Brianna.
Thank you, Jerry and Orling, for your demonstration. So now we'll see what's to come with DDR5. Over to you, Jerry.
All right. So with DDR5, so the new technology, DDR4, has reached some limitations. Each of the families has improvements where you can increase the speed, but they do have their limitations. DDR5 is primarily driven from the increased need for bandwidth in the new multi-core computers that are being developed today. So as you increase the number of cores in each of the processors that those machines are designed with, each of those particular cores requires more and more bandwidth for access to memory. So it's going to present even more challenges that DDR4 is not going to be able to satisfy. So they're looking at DDR5 now for speed enhancements, speed improvements, as well as power reduction again. Same themes: faster, bigger, and less power. So some of the changes in the DDR5 obviously are the faster speeds. You're going to again see a doubling of the data rate. Densities again will be increased up to 64 gig is what the plans are now. Supply voltage will be reduced down to 1.1 volt now, as opposed to 1.2 in DDR4. The VPP level for the internal write buffers will be 1.8 volts, and they're going to add some more equalization on the receiver end. So you saw me add the algorithmic modeling interface in the demo on the receiver for a write operation. The receivers in DDR5, in addition to having this ETLE capability for AMI, they will also now support DFE. So that will be available in the DDR5. Some of the duty cycle adjustments that you saw in DDR4 are going to be enhanced for the DQ and DQS lines with enhanced error checking. On-die termination, the dynamic on-die termination and bus inversions are going to be extended to the command bus in DDR5. So in particular, bus inversion. So that capability of saving power and inverting the bus for when you have a majority of zeros in transmission you'll be able to take advantage of that in the command bus, the address bus access. There's also been some improvements in write leveling and retraining and the refresh and recharge commands, as well as a loopback mode for testing for DQ and DQS line testing. So out of those, let's take a look at just a couple of things that they've focused on to generate faster speeds and just quicker access times. One of those is they, rather than just rawly increasing the number of banks per group, they're increasing the number of bank groups themselves. And what this basically allows is it allows them to take advantage of the faster access times for between bank group to bank group. Typically, bank to bank is the longer access time, and so when you have a shorter access time, or rather have more bank groups that have short access times, you typically, since you have more of them, you're going to have a more of a probability of utilizing bank group to bank group data exchanges. So with that being the case, then they can take advantage of the shorter timings between the bank groups themselves and not have to go bank to bank where they have a longer access time hit. Another thing that's going to happen is burst length is going to be increased to 16. And what this does is it provides larger internal access to the array, and therefore they don't have to take the timing hit of going through the IOs to transfer that data from the internal memory array out to the IOs. They only have to do that one time, 16 words at a time. So if you're having to access smaller word sizes to get these larger sizes out, you're going to have to go through multiple timing hits of the IOs because you're accessing the array and bringing that information out multiple times. With the wider access, it's less amount of timing exposure to that. It also allows for a new DIMM configuration. So you can use two independent 40-bit channels now for the DIMM designs, which basically allows concurrency between each of the channels and essentially doubles the number of available memory channels for each of the particular DIMMs. And that in and of itself will increase efficiency and speed for those particular memory arrays. Another thing they've added is the concept of a same bank refresh. In the past, it's usually you're refreshing the entire array or larger aspects of the array. With the same bank refresh, you get a much faster refresh time, and basically what that amounts to is the problem of when you're going through refresh, any bank that's refreshing cannot have any data exchange happening. So it has to be, number one, it has to be idle in the first place, and then number two, once the refresh finishes, there's a recovery latency time that has to be wait. You have to wait a certain amount of latency time before you can begin to access that bank again. With the same bank refresh, that access time is much shorter. So what this allows is you can refresh each bank or a bank in each bank group all simultaneously, while the other three banks in the group still have access to be able to exchange data. So it gives you a much more efficient process of refresh, and allowing, the higher efficiency allows much faster run rate for the devices. So just to wrap up, as these protocols evolve for memory technologies, so do the complexities, because what you're doing is increasing speed, lowering power, trying to get more efficient, faster operating devices, and it leads to the speed increase makes you move into areas of physics of the board and everything that you have to really understand what you're designing with, and be able to understand how to design with those particular speed grades and technologies. It's basically very critical to your design success. Tight timing margins and the lower power thresholds, for noise to be present, reduce the margin available for timing. So you have to basically go through your very restrictive layout techniques, and then design and verify your DDR in simulation once you're done. So overall, the point here is that we can provide you the tools and support for your DDR design efforts with simulation tools, first-class simulation tools, as well as first-in-class layout and placement and layout tools for your PCB development.
All right, thank you, Jerry. At this time, I would like to open up the floor for the Q&A. So please enter any questions you have into the chat now. If we are unable to address your questions immediately, we will be in contact with you. Just a reminder to all attendees that this webinar will be recorded and posted on the EMA website with the slides within the next few days. So I have a question for Orlin here. What are the most important parameters for defining the stack-up material property and physical dimensions to achieve picosecond accuracy for timing and accurate impedance levels? What if the PCB fab house deviates from your modeled and simulated configuration?
That's a good question. If the board house does deviate from that, that can truly mess up your design. Of course, you have proof that they deviated from it. They're going to eat the cost of those boards, and I've known a few board houses to have to do that. Stack up is very important. A lot of times I will recommend going to that board house up front, getting that stack up, telling them the impedance you want to hit. They'll make sure the pre-preg material in the ground plane is adequate to meet your impedances that you need. So it's a concurrent engineering with board houses now, also not just with mechanical engineering and electrical engineering. Everyone has to be involved and everyone needs to have input into it. I hope that answers your question.
Thank you, Orlin. So I have another question for Jerry. In regards to DDR timing analysis, those are calculated values and data. Actual values may be different due to manufacturing deviations. So how much margin is needed within the calculation so that any deviation or errors won't affect timing?
Well, margin is part of kind of part of the spec. So you're going to see what what margin. The spec is essentially going to give you the absolute minimum requirements that you need to meet. The amount of margin you're going to have to meet that within is based on your layout, how much how much attention you pay to stack up, to your layout, to your routing, and then even then, if it's very minimal, you can get away with getting a little bit more margin by using some of the AMI modeling interfaces that are available for the receiver arrays. So hope that answers your question adequately. Margin is kind of a relative thing in terms of the specifics of your layout.
Thank you. So we have one more in regards to the topology. So we have someone who's used to the flyby layout. So what was the type of layout that was used in this demonstration?
Okay, yeah, in this, what I was laying out was actually the leveling. So I had a buffer in there. The buffer's built into the processor. So the placement was done, and the flight time was from driver to receiver. You don't really need to take account anymore of determination, although the termination, as short as possible is the variety there. But yes, I did have a register in there, and it was built into the processor, and then I laid out accordingly.
Thank you. So one more question for Jerry. We're running a little low on time here. In regard to the simulation, in addition to board parasitic, I presume Sigrity imports the board Stackup as well?
Yes, it does. In the demo you saw, I went to the Stackup editor and kind of showed you the layout, or basically the Stackup relative to the layout. The Stackup comes in, that Stackup information comes into the Sigrity tools via the board database. So from Allegro, it would be in the .brd file, the board file. So that Stackup information, that's where it starts. Of course, if it's not complete or you need to have more details in the Stackup than what was necessary for layout, you can certainly add and embellish the Stackup for terms of figuring out whether or not that Stackup's going to work for your simulation parameters. So it's a full-on editor that's in the tool. The original starting point comes from the database.
Thank you. Well, looks like we still have questions coming in, but unfortunately we are running out of time. But if there's any questions that we were not able to address during the webinar, we will be following up with you on an individual basis. Before we sign off, I would like to inform you of our next webinar, PCB Data Management Fundamentals. So keep an eye out for more information on that webinar. Thank you for joining us for today.